Hey, this is Mr. Aiden. This is AP Chemistry, Unit 6 Thermodynamics. We're going to do a little wrap-up today, and we're going to be bringing the heat. So just a little wrap-up of everything in thermodynamics in this entire unit, Unit 6. So let's get to it. So what I want to do today is take a look at a little bit more of the particle nature of thermodynamics and just bring everything together. So let's take this piece of iron, okay, and we're going to heat this piece of iron up. I'm going to show you the energy that's in here, and we're going to kind of take the temperature of this iron, and we're going to heat this iron up to as much heat as possible. Now you can see this heat is pouring in energy. It's pouring in energy, and what's happening to the particles of the iron? The particles of the iron are moving faster. Now think of these particles. I really want you to think of the particle nature of what we have here. And these iron atoms have delocalized electrons, of course, and these iron atoms are moving with a high average kinetic energy, okay, which means the particles are moving fast. They're moving with a high average kinetic energy, a high average speed, and even though these particles are close together, metallic attractions, they're moving with high kinetic energy. Okay, and so I'm going to put a little bit more energy within this to keep that temperature up high. And so the water right here, I'm going to put the water on this little plate as well. And the water has a lower average kinetic energy. So this water is at a lower absolute temperature, and so this has a lower average kinetic energy of the water molecules. The water molecules have hydrogen bonding attractions, and so watch what happens as I put this piece of iron inside the water. You can see how the iron released energy to the water molecules. The water molecules absorbed energy, and so the iron here, the Fe, released was exothermic, whereas the water molecules, the H2O, was endothermic, and the water gained energy. The energy that they exchanged, the average kinetic energy that they exchanged was equal. So the kinetic energy that the iron released was equal in magnitude to the kinetic energy that the water absorbed. Okay, and so the magnitude is exactly the same. And you can see they came to an average, an equilibrium, what we call thermal equilibrium. Thermal equilibrium, which means they came to the same absolute temperature, which means the water and the iron both have the same average kinetic energy. And so we can see what happens there. Now, the iron went down a huge amount of temperature. The water went up just a small amount of temperature. And that's because the specific heat of water is 4.18 joules for every gram degrees Celsius, or degrees Kelvin. Or Kelvin, not degrees Kelvin, but Kelvin. The iron has a specific heat of 0.450 joules for every gram degrees Celsius, which means, do you see how the iron, because it's a better conductor of heat, it only takes 0.45 joules of energy to make 1 gram change 1 degree Celsius, whereas the water, it takes 4.18 joules of energy to make 1 gram of water change 1 degree Celsius. So the temperature change is very different, but the average kinetic energy that they exchanged was exactly the same. And so they had the exact same magnitude of heat energy. And so the water molecules, think about the water molecules will have moved with a faster speed, a faster kinetic energy, because it gained energy, whereas the iron particles, the atoms, are going to move at a slower speed. They moved with a slower amount. And so even think about what's happening when I take this iron out, and as this iron begins to heat up again and the particles are moving faster and faster and faster, you can see how the iron is absorbing heat from the surroundings, and the surroundings is losing heat. Now the iron, you can see some of those heat particles are coming off. Those heat are coming off, not particles, but heat waves, and the iron is losing heat to the surroundings, and the surroundings are gaining heat. So anytime you're thinking about this heat exchange, you want to think about it in terms of endothermic and exothermic. And so let's go to just straight water molecules here. These water molecules are at a liquid water, okay? And so you can see this, we have an H2O liquid right here. This H2O is at 298 Kelvin or 25 degrees Celsius, 25 degrees Celsius right here. And so it is a liquid. Okay, and so in order to make this water become H2O gas, some things have to happen. We have to bring this up to 100 degrees Celsius, or we could say 373 degrees Kelvin. Okay, that is a 75-degree difference. We have to change the temperature at 75 degrees Celsius, or you could say 75 Kelvin as well. And so the change in temperature of 1 degree Celsius is the same as a change in temperature in Kelvin. So we have to heat that water up to 100 degrees, the boiling point of water. But then what do we have to do is, remember, that's still a liquid there. We have to boil that H2O gas, which is still going to be at 100 degrees Celsius, 373 degrees Kelvin. But we need to break all the hydrogen bonding attractions here. We have to break the hydrogen bonding attractions. And we have to break all of those hydrogen bonding attractions. Once we break all those hydrogen bonding attractions, the entire substance will be a gas. And now the temperature can go back up. And so let's think about what's happening here. When it's a water, when it's H2O liquid, we can use the formula Q equals MC change in T. Okay, let's say we have 1 mole of water. Okay, 1 mole of water, which would equal 18 grams of water. So we have 18 grams of water. The specific heat of water is 4.18 joules per gram degrees Celsius. Okay, and the change in temperature is going to be 75 degrees Celsius. 75 degrees Celsius. Okay, and so you can see what's happening here is the water needs to absorb heat. And so when I calculate that the heat that the water needs to absorb is 5,643 joules, or 5.643 kilojoules of heat. Now that's the kilojoules just to get it up to 100 degrees Celsius. Then we need to break the hydrogen bonding attraction. So let's first pour in that heat there. So we're going to pour in this heat. So we're heating this up all the way to 373 degrees Kelvin. 373 degrees Kelvin. And so you can see how, there we go, perfect, 373 degrees Kelvin. So I poured in 5.6 kilojoules of heat just to get it to this temperature. Now, as I continue to pour in heat, it's going to start breaking these attractions. You can see as the change of temperature changed, the particles are moving faster with a greater average kinetic energy. But now the energy, or the heat, is going to go into breaking attractions. So I'm going to erase all of this if that's okay with you guys. It sure is, because you're at the mercy of my hands here. And you can see how now to go from H2O liquid to H2O gas, remember, we're at 100 degrees Celsius. We're not changing the temperature. We need to make what's called a physical change. This physical change is breaking the hydrogen bonding attractions, the HBA, the hydrogen bonding attractions. And that is called the heat of vaporization, the heat in order to vaporize this water. And the heat that vaporizes this water is 41 kilojoules per mole. It's kind of like your 4.18 number. It's a known. It takes 41 kilojoules of heat to heat up and boil and break 1 mole of the hydrogen bonding attractions. So think about it. When we add these two numbers together, to get it from 25 degrees Celsius all the way up to 100 degrees Celsius, and then boil every single one of these particles, we need to put in, if we add these two numbers up, we need to put in 46.643 kilojoules to do 1 mole there, to do 1 mole. And we have 1 mole. If it was 2 moles, it would be double the amount of heat. And so that is the amount of heat to boil every single one of these. Then, once we boil everything, now it's all gas, and now the specific heat of water as a gas changes, and now we can change the average kinetic energy again. Okay? And so what's happening there is, if we kind of think about this logically, is right here we're at 25 degrees Celsius, and we are going to pour in heat. We're going to pour in heat to bring it up to 100 degrees Celsius. Now we need to pour in a lot of heat. Remember, that only took from here to here. That only took about what was that again? That was about 5.6 kilojoules of heat. But then you can see it takes 41 kilojoules of heat to boil all of it. Once we boil all of it, now the temperature can begin to rise again as we continue to pour in heat. Keep in mind, it also takes 41 kilojoules to release, to condense it. So if it takes 41 kilojoules to boil it, 1 mole of water, it's going to take 41 kilojoules releasing to condense it. So if it releases, you can see as we release heat here, you can see it becomes a liquid water again, and the particles are going to move slower and slower and slower. Okay? And let's take a look at dissolving salts. Okay, so let's take a look at a salt like sodium nitrate, and we're going to dissolve this salt, 5 grams of this sodium nitrate, in 50 milliliters of water. And so as we begin to dissolve this salt, you can see the temperature of the solution is going down. The water is getting, quote unquote, colder, which means the water is releasing heat, isn't it? Okay? And so the water is exothermic, which means the solution itself is endothermic. So let's think about what's happening particle-wise here. So we had sodium nitrate, NaNO3, and as we put this in water, it broke the ionic attractions, Na and NO3. It turned it into ions, okay, which are now conductive because these ions are free. But these ions, think about it, to break these ions, it was positive energy. It was endothermic, wasn't it? To break any kind of attractions or any kind of bonds, these aren't quite bonds, they're more attractions, Coulombic attractions, it always takes energy. Now, think about it. We also had to break the hydrogen bonding attractions with the water. We had to break the hydrogen bonding attractions with the water, which is also endothermic as well. But then the water molecules, the H2O water molecules, are making attractions with the sodium ions and the nitrate ions, and we call those ion to dipole attractions. And when we're forming attractions, it's negative, it's exothermic. Okay? And so we can see what's happening here is this, whether this reaction is endothermic or exothermic, it's whether these positive numbers are bigger than the negative, or the negative is bigger than the positive. Okay, so let's take a look at the math behind this. Okay, the math behind this. So we had 5 grams of NaNO3. Anytime we have grams, what do? We divide by the molar mass. The molar mass of NaNO3 is 85 grams per mole, which leaves us with 0.0588 moles of sodium nitrate. Okay. Now, we can say the solution, if we want to find the heat of the solution, we have to use the mass of the solution, the specific heat of the solution, and the change in temperature of the solution. We have to stay consistent. So the mass of the solution was 50 grams of water and 5 grams, which is 55 total grams. 55 total grams. Okay? The solution is mainly water, so it still has a specific heat of 4.18 joules per gram degree Celsius. And look at the change of temperature in the water. Change of temperature in the water was negative 5.63 degrees Celsius. So the heat of the solution was negative 1294 joules. Okay? The solution was exothermic, or releasing heat, which means, or we could say the water itself was releasing heat, wasn't it? Which means the solution must have been absorbing the same amount of heat. It must have been absorbing 1.29 kilojoules for every 0.0588 moles, which means we can think about that as positive 22 kilojoules per mole. So when the water got cold, that was because we had an endothermic solution. And that is what we call the enthalpy of the solution, isn't it? Okay. So let's take a look at an exothermic solution. Okay, so we're going to close this out. We're going to reset it. We're going to take a look at NaOH, 5 grams of NaOH in 50 grams or 50 milliliters of water. And look at this. The temperature is going up in this solution. Okay, so again, what's happening? The NaOH is dissolving and becoming Na plus and OH minus. The water is breaking apart the hydrogen bonding attractions. Those are all positive endothermic. And then we're forming attractions between the Na plus and the OH minus and the water molecules, right? We call that ion to dipole attractions. We're forming attractions. That's negative, that's exothermic. Now in this case, the exothermic is much greater because look at the temperature change. The temperature change is going up. So let's look at the math behind this. We have 5 grams of NaOH. We're going to divide that by 40 grams per mole. That's the molar mass of NaOH, which ends up being 0.125 moles of NaOH. That's what we use. Okay, and let's take a look at the Q of the solution. The Q of the solution, we got to use the mass of the solution, the specific heat of the solution, the change in temperature of the solution. The total mass is 55 grams. The specific heat is 4.18 joules per gram degree Celsius, and the change was positive 24.19, wasn't it? Because the temperature went up, which means the solution, think about it, was positive 55.61 joules of heat. So the water absorbed 55.61 joules of heat, or you could say 5.561 kilojoules, which means if the water is absorbing that, the solution must be releasing it. So the enthalpy of the solution is not positive, but negative. This is an exothermic solution, right? It got hot. 5.561 kilojoules for every 0.125 moles, and that ends up becoming negative 44.5 kilojoules per mole. That's the enthalpy of solution of sodium hydroxide there. Okay. Now let's take a look. We're going to go to our bonds. We're going to take a look at bonds. And first, let's take a look at the chlorine, a chlorine bond. We know chlorine is a single bond. And think about this chlorine single bond here. Okay. This chlorine single bond is, and I'll put this right here, Cl2. Okay. Look at this chlorine single bond. And you can see, if I come down to the bottom right here, where the attraction repulsion of the atoms are minimized, you can see it takes 240 kilojoules to break one bond. Okay, so it always takes energy to break these bonds. And look at the bond distance. It's 2 angstroms. 2.0 angstroms is the distance of this bond. It's a really, 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 really long bond. Okay, so let's load a different one. Let's load a double bond. Let's load oxygen gas, and let's take a look at oxygen gas. Okay, and as I take a look at oxygen gas, you can see to break one of these bonds, it takes, let's see, O2. I'm gonna put O2 right here. O2 is a double bond. It takes 494 kilojoules to break one of these double bonds. And look at the distance. The distance is approximately about 1.2 angstroms. Okay, it's a shorter bond, but it's a stronger bond because it's a double bond. And it takes more energy to break this bond. And you can see, using the simulation, if I put in that energy, you can see it broke that bond. It broke that bond there. And so it also takes the same amount of energy to form the bonds, but that would be a negative energy, wouldn't it? Now let's go to the last one. Let's go to nitrogen gas there. Nitrogen gas is a triple bond. And let's take a look at the energy to break one nitrogen gas triple bond. It takes, ooh, I almost got it right there. Oh, it's so close, so close. Oh, come on, baby. There we go. Oh, man. There we go. To break this one nitrogen gas, I'm going to put that in a different color, one nitrogen gas, it takes 942 kilojoules to break that triple bond. And so it would also take 942 kilojoules given away, exothermic, to form that bond. And look at the angstroms, 1.1 angstroms. It's a shorter bond, but it is a stronger bond to break those bonds. And so in any chemical change, we need to break bonds. In a physical change, we're just breaking attractions. But in a chemical change, we are breaking bonds. And so here we have a 120 atom model. You can see the red ones are fast, the blue ones are slow. And what do we have here in the fast atoms is they're at a higher temperature, which means they're moving at a higher average kinetic energy, aren't they? Whereas the blue ones are at a lower temperature, which means they're moving at a lower average kinetic energy. And so you can see we have these guys separated, but we're going to take away this insulating wall. And when we remove this insulating wall, I hope you're going to see what we're going to see is as these particles collide together, they're exchanging energy. And you can see how the temperature in Kelvin is going down for one, it's going up for the other. The kinetic energy is going down and it's going up. And the average kinetic energy is exchanging perfectly. It's perfectly. As one is losing energy, the other particles are gaining energy in the collision. And they come to that thermal equilibrium that we see. Thermal equilibrium means approximately they're coming to the same average temperature, and they're coming to the same average kinetic energy, aren't they? And so you can see they come to what's called thermal equilibrium through collisions. And that is in any kind of chemical change. We have our bonds here, don't we? And we can look at this in many different ways. But the one way you can see here we have methane is CH4, okay? CH4. And so we have to break 4 of these carbon to hydrogen bonds. And we have to break 2 of these oxygen-oxygen double bonds, don't we, in our O2 molecules. So we got to break these bonds. And so in our CH bonds, just one CH bond is 411 kilojoules to break one of these. And you can see oxygen-oxygen double bond, to break that is 494 kilojoules, if you remember when we looked at the bond enthalpies. Okay? And so we have to break 4 of these. We have to break 2 of these, don't we? And that's the activation energy going into breaking bonds. And not only do they have to hit with the right amount of energy, but they have to hit the right orientation as well in order to break these bonds. And you can see that is the activation energy. And so I'm going to kind of erase that. And that is the activation energy that we put in to break the bonds. And then you can see when we form new bonds, we are forming a couple new bonds, aren't we? We're forming our bonds right here. We're forming 2 of these carbon to oxygen double bonds, which those forming are negative 799 kilojoules. And we're also forming, you can see, count them, 4 of these OH bonds. You're doing 4 of these. And to form these is negative 459 kilojoules of heat. Okay? And when you sum up all these bonds breaking and all these bonds forming, it gives you the enthalpy for the reaction. And the enthalpy for the reaction ends up becoming approximately negative 803 kilojoules for every mole, okay? And that is using bond enthalpies in order to take a look at that. We could also take a look at it in a different way. We could take a look at it as the heats of formation of my reactants and the heats of formation of the products. Which, remember, the heats of formations using the enthalpy of the reaction is we sum up all the heats of formation of our products minus all the heats of formation of our reactants. And remember, we're using our products and our reactants for that. Okay. If you take a look at O2, the enthalpy of O2, it's 0 because they are elemental substances. But the heat of formation of CH4 ends up becoming, I think it's like negative 74. Oh, yeah, it is. It's right there, negative 74. So negative 74 kilojoules per mole for my reactants. And then you can see we can also take a look at the heats of formation of my products. If you took a look at the heat of formation of my products, I'm talking about the heat of formation of my carbon dioxide and the heat of formation of my water, gaseous water that is, because it's gaseous water. If I add up all of these heats, and we're talking about 1 mole here, and we're talking about 2 moles here, and I add up all of that, the heats of formation of my products are negative 877 kilojoules. How do I know that? Well, it's right here. Okay. I could also take a look. The heats of formation of carbon dioxide is, I believe it's negative 393.5. And this guy for gaseous water is negative 241.8. You multiply that by 2, you add them all up, you're going to get negative 877. Just double check me on that. I'm pretty sure I'm right. And so you can see when I add up all of these using this heats of formation, I get negative 803 kilojoules per mole. I get the exact same amount, whether I'm doing it by bonds or whether I'm doing it by heats of formation. We can find enthalpy in so many different ways, but we have to look at all of our thermo as in a particle nature and think about what's happening with the heat exchange, what's happening with what's exothermic, what's endothermic, what's happening particle wise. Is it a physical change, just breaking attractions, or is it actually breaking bonds in a chemical change? And that was us bringing it hot, bringing the heat, thermochemistry, wrapping it all up. Have a good Christmas. I'll see you guys on the other side of the year.